Welcome everyone here, both in Łódź as well as connected remotely all over the world. We have three extremely exciting papers today. One presented from Japan remotely, and two presented here on site, which is also very nice. We have this session. My name is Sebastian Feger. I'm from LMU Munich. I'm chairing the session today, and the session is on pointing and decals. So we will learn about how to interact with information and how to reorganize and arrange information in different ways. So without further ado, I would invite the first speaker who is connected remotely, Hiroki Usuba from Meiji University, Japan, to talk about uncertain touchable sizes.
Hi, I'm Hiroki Usuba. I'm a PhD student at Meiji University. Today, I will talk about a study titled Modeling Movement Times and Success Rates for Acquisition of One-Dimensional Targets with Uncertain Touchable Sizes. In graphical user interfaces, a target has a visual width and a touchable width. The visual width is the area in which a target is displayed on the screen. The touchable width is the area in which users can touch a target. For example, in button A, the visual width is smaller than the touchable width because the button background is transparent. In button B, the visual width equals the touchable width because the background is colored. In button C, the visual width is larger than the touchable width because the order of the span and anchor tags is reversed, and only text is a hyperlink. In realistic touch interfaces, of course, the visual and touchable width exist. For example, in iOS settings, the visual width equals the touchable width because the items are split with horizontal lines. So users aim between the horizontal lines. On the other hand, in the Gmail sidebar, the visual width is smaller than the touchable width because the items are not split. So users cannot determine the exact size of the touchable width from the target's appearance. In this situation, two strategies exist. If the users have used the application several times, they aim for the touchable width than through use. If the users are using the application for the first time, they may assume the visual width is touchable and aim for it. In this study, we investigate the effects of the visual and touchable width on touch pointing performance and build models for predicting this performance. Existing models are limited to situations where the visual and touchable width are equal. The objective of this study is to address this limitation. We test two situations. One is when users roughly know the touchable width, and the other is when users do not the size of touchable width. The former is operations in frequently used applications, and the latter is operations in applications being used for the first time. Experiment 1 simulated operations in frequently used applications. This experiment consisted of two blocks, the exploration block and data collection block. In the exploration block, the participant taps the blue start bar and then somewhere around the green target bar. Thereby, the participant memorized and explored the size of the touchable size of the target. In the data collection block, the participant taps the start bar and then the touchable width of the targets that the participant memorized. In the experiment, the participant repeated the two blocks and the experimental conditions. The experimental conditions was shown on the screen. There are one type of the distance to the target, 4 types of the visual width, and 4 types of touchable width. So the visual width was larger than, equal to, or smaller than the touchable width. As a result of the experiment, we found the movement time depended significantly on the visual and touchable width. So increasing the visual or touchable width decreased the movement time. These effects of the width were consistent with that of the width of the pit task. On the basis of the results, we built several movement times models. The beta model shows lower ASC and higher adjusted R-squared. Model 3, which is the model of mass pointing, shows the lowest ASC. Model 7, which is created by combining Model 3 and Collateral's F-fits law, showed highest adjusted R-squared. The difference of the ASC and R-squared between models 3 and 7 was small, and model 3 had fewer parameters than model 7. So model 3 was the best model among the candidates. The success rate is predicted by predicting the touchpoint distribution. We found the standard deviation of the touchpoints depended significantly on the touchable width. Increasing the touchable width increases the sigma. Again, we found increasing the touchable width increased the sigma. Plus, in the task, when the touch point fall in the touchable width, the trial was regarded as a success. So, on the basis of the fact, the previous model can be converted as shown on the screen. The cross-validation showed a low average MAE. The results were comparable to those of the previous studies. Next, experiment 2 simulated operations in applications being used for the first time. So, unlike experiment 1, this experiment consists only the data collection block. Plus, the visual is smaller than or equal to the touchable width. As a result of the experiment, we found the movement time depended significantly on only the visual width. So, increasing the visual width decreased the movement time. On the basis of the result, we built several movement time models. Model 1, which is created by replacing W in Fitts law with the visual width, shows the lowest ASE. Model 1, 5, and 6 show the highest adjusted R-squared. Model 5 was created by replacing W in Collateral's F-fits law with the visual width. Model 1 had fewer parameters than models 5 and 6. So, Model 1 was the best model among the candidates. Next, we found the touchpoint distribution did not depend on the visual and touchable width. So, the sigma was constant. Again, in the task, when the touchpoint fell in the touchable width, the trial was regarded as a success. So, on the basis of the fact, the previous model can be converted as shown on the screen. The cross-validation showed a low average MAE. The results were comparable to those of the previous studies. Based on the result, we built a design implication. In operations in frequently used applications, we found the movement time depended on the visual and touchable with, and success rate depended on touchable with. In continuous tapping applications, for example, shopping and game applications, the movement time is important. So your designer should make the touchable size as large as possible and make the target's appearance clear. On the other hand, applications where one tap is important, for example, the Gmail sidebar, the success rate is important. So your designers should make the touchable size as large as possible. Next, in operations in applications being used for the first time, we found the movement time depends on the visual width and success rates depended on the touchable width. So your designers should make the target's appearance and touchable size equal and make the target as large as possible. For example, the designers must avoid showing the target's only an icon, and they should fill the background of the target. This is the summary of the presentation today. Thank you for listening.